Welcome, everybody, to our lecture on machine learning. Hope you're doing well. You might have seen that you are now registered for the Moodle course. You have all access to the material of this course now. The recording of last week is already uploaded. Today's recording will be also uploaded, so whenever you miss some event, you can have a look at the video. The only drawback of the videos is simply the recordings, that whenever I present something with slides, then I switch to the blackboard. This is really hard to see because what you see in the WebEx recording is the screen of the laptop. Maybe the camera of the laptop that points towards the blackboard, but then what I'm writing, it's really hard to see. Are there any questions regarding this course from your side? Then I would like to present the first quiz to you. Quiz. Why is this now? Okay. So this is the first quiz of this lecture. Oh, sorry. You have not seen any slide, so now you see slides. Forgive me. You will see a QR code and a link. Yes, here we go. Oh, this is the wrong one. Ah, I see. So here you see the link. It's always tweakback.de/ and then there is the code for this quiz, for this session. In this case, it's called und_m. You click on the link. There are 2 questions. Both are activated. Here's some guideline. Be aware that take care for answering these questions. Typically, you only get bonus points if you have everything correct. If there's a single mistake, one of the answers is wrong, you get no points. Today, you have the option to get 2 bonus points. I have here the list as promised. There are 79 enrolled students, so I had to print it double page, and maybe it's a bit tricky to find the right column, but today it's still easy. I will hand it out. We discuss the correct answers afterwards. And if you have one of the 2 questions right, you get 1 point. If you have 2 right, correct, you get 2 points. And you simply add a 1 or a 2 next to your name in the column where it says 12th of March. Give that to you. You see, I only have 5 printed copies with me. After the lecture, I will collect the student list and then we will add the numbers to Moodle, your bonus points. The other benefit is on this list, you also see all the dates that we have, dates for the lectures, for the exercises, for the assignments. And here you see also the submission dates of the assignments. If this list would be very helpful for all of you, I could send you one without names. I can do that. Taking copies of this list might be some data, cause some data issues because they're all names of all colleagues here. If you would like to have the list, I can send it to you without the names. Otherwise, we have the dates anyways on the slide. So the first question is about machine learning. The second one is about the course. So actually these questions are not so difficult, probably. They will become more challenging. In total, there should be about 20 bonus points for this course. And if you look at the sheets, you see that we have about 220 points in total, and you need around 190 to get a 1. Officially, all bonus points count to the exercise parts. But in the end, you get 1 certificate. There was one confusion last time. I presented all these exam dates for the written exam. There's a single written exam you have to take if you pass. But of course, there are multiple dates. By law, I have to provide you the opportunity to attend 1 out of 6 exam dates during the year. So 3 dates are now online, and then we will find out how many students still need a date. You typically send me an email then. But the student asked me if he needs to take all 3 exam dates. I say, no, only a single one is fine. Give you some more seconds. On Friday, we will have our first programming exercise in the lecture room upstairs. This programming exercise might be for real beginners. If you never used Jupyter Hub notebooks, you never programmed in Python, you're welcome to join. We will create accounts for you. At least 12 students already did that. You can do that already now. You have the link in the slides from last week. Otherwise, we do that next Friday. These accounts will be used for your assignments and for everything, for the exercises. Are you all done? Let's have a look. This is the wrong, this one. Here I tell you, 48 of you got it right. Machine learning is a branch of AI focusing on the design and development of algorithms that allow computers to learn. Perfect. Who knows how the other answers have been created this morning? Guess? Yes. This is my assistant. Normally I think about it myself, but sometimes for these general purpose questions, it's fine. So the second one, yeah, is a bit more tricky. You see it here from the statistics. 40 of you got it right. This is the right answer. So, sorry, answer number 4 is correct. There's one final written exam. There are 4 mandatory assignments, and there's 1 computer programming exam. It's true that there are 5 assignments, but one of them is a bonus point assignment. This is not necessary to submit to pass the course. A bit tricky. Please add your bonus points to the list. You will have more options during the course. Do you have any questions? Just interrupt me whenever you want. It's all fine. Yeah? Today, I will present some important machine learning examples to you. And we will find out that these examples belong to 1 out of 3 categories. In machine learning, we typically talk about supervised learning algorithms, unsupervised learning algorithms, and reinforcement learning algorithms. And today, you will learn what is the difference between these 3 categories or types of machine learning algorithms. So you will understand how these different types of machine learning algorithms actually work. Here's a popular example of using some AI system to generate artwork. That's DALL-E. You can try it out yourself. That's really impressive what the guys of OpenAI are doing. You all are using nowadays foundation models like language models, so you know the game. You know that I really force that you use AI systems, use it for learning. It will help you a lot. Make sure that whenever you create content and you submit it, that the creative part had its origin in your brain. So good scientific practice is the keyword. Here you need to find your way how to best work with AI systems. If you write a bachelor thesis, you will use it to improve your text, to improve the spelling, everything. That's all fine. Just make sure that you tell your supervisor and that everybody's informed. For official documents like the master thesis or PhD thesis, you have to even announce it. In the end, there's a table where you need to specify which tools you used and how you used it. Well, I'm a big fan of NVIDIA's Playground. So this is a very exciting platform to use new AI systems. I skipped that here for a moment. Last year, I used the AI system here to generate some artwork of how I would see ourselves here in this lecture room, how I could improve the logo of the chair or whatever. But let's start with some concrete examples. I'll give you some idea of different machine learning algorithms. The first one is a very important approach. It's called an autoencoder. Who knows what is the key idea of an autoencoder? Any idea? So nowadays, people use variational autoencoder. But what is the key idea of an autoencoder? If I tell you that it has to do something with a sand clock, would you have then an idea? If you have a sand clock rotated by 90 degrees, it would look like that. That's where the data goes in. That's where the data goes out. And if you do that, all the data has to pass through some narrow passage. And that's the key idea of an autoencoder. An autoencoder tries to reconstruct the inputs here at the output side as best as possible, while making sure that all the data has to pass through this narrow passage, which is a kind of a compression strategy. So you're compressing the data, you want to reconstruct it, the output should be exactly the same like the input, but you want to compress it in such a way that you can model it in the end using a few parameters here in the center. Let's have a look at a more descriptive explanation. So the key idea is to regenerate the original input data from a learned, yes, numbers, integer numbers. Yeah, it's a bit hard to see because if you flip it, it's also okay to fold it to see which column you need to use today. If you use the wrong column today, we will fix it when we add it to the digital spreadsheet. Normally, you just add a 0. You don't need to add zeros. Add ones or twos. That's fine. And add it next to your name, even if you add it next to your name immediately. I will print this sheet every week, fresh. So it doesn't matter if you put your one somewhere along this row. Put it next to your name.
Number is the number of questions I could write in the.
Exactly.
Okay, thanks.
And the maximum number is written in red on top. So if you put 20, it won't help you. But it's a good point. The best is simply to add the number next to your name. Then it's also easier for us to edit afterwards. Maybe I create a separate column next to the names just for the current date. Very good idea. Like it. So the key idea is to regenerate the original data using some low-dimensional encoding. What does that mean? Encoding sounds difficult. What do you think? Or with some code. And encoding is always a representation in the computer science language. So you will get used to this language throughout the course, but ask me. If you hear some term for the first time and you really get confused, ask me. Encoding could be a binary code, for instance. So you have letters A, B, and C, and your encoding is a binary code. Whatever. Could be, for instance, if a neuron is active or not, a spiking neuron. Spiking neurons are special neurons that initiate a spike to communicate data. So this is a representation of this three letter or an encoding. So the key idea is that if we force that all the data has to pass through this narrow passage, we assume that by that we remove all the noise that is not important to reproduce the data. So let's say you have an image, or let's say you have a video of something, and it's very noisy, your camera image, it's dark or whatever, but there is a single object in the image and it's static. And then you try to model that using an autoencoder. What the encoder will do is, if you use just a few neurons here in this center, it will remove all the background information. It will remove all the noise from the dark image. And what will remain is the single object in the picture. And that's what you want. So that's how you would see it in some research papers. This is from 91. So this idea, it's pretty old already, but it's now a very important concept. You see here that the inputs are denoted by Y1 to Ym, and the outputs are denoted by Y dash. The reason is that in the end, they should represent the same. And what you will do is you create an error signal that where you subtract Y minus Y dash. And your learning signal is based on the error. So we'll update all these parameters in this model based on the error. And your goal is to minimize the error. So input should be equal to the output. And what you will then do as an engineer or as a machine learning expert, you will say, okay, let's start with a larger network where the compression rate is low. Let's say you use 10,000 neurons. And in your middle layer here, this one is the narrow passage here. You use, let's say, 300 neurons. Then you look at the error, you look at the signals, and then you try to reduce this number, the number of neurons in this middle layer, until you only have 3 neurons left, or 4. Something like that. And then you will see that the error will increase, of course, but you will also look at the data, and at some point you will say, okay, this is the optimum. So generally speaking, just to give you a rough idea. Let's look at an example. Here, this is the example of the original paper. What you see here is the original image, the reconstruction using a single architecture. Now, this is also maybe some new word. Architecture in the concept of neural networks means one single type of neural network where we decided we have 3 neurons in the center. This is an architecture. Who knows how you decide how many input neurons you need? Exactly. Yeah. So this is the easy part. How would you do it for the data that we see here? Exactly. Totally right. Everything is correct what you said. For this particular example, it's a bit simplified. Here you only have grayscale images, so you don't have red, green, and blue as color channel. You only have a gray channel. And then these numbers typically range from 0 to 255. Who knows why? 8-bit system, exactly, yeah. And if you start with 0, you have 256 numbers, then you have 8 bits. So in this grayscale image, you have maybe a very low resolution. I don't know it. We would need to look it up. It's the MNIST data set. It would be defined anyways on the MNIST page, probably around 100 or 200 times something like that. So 200 times 300 is the image resolution. Then you put everything together in a long vector, and this is your input. So every row, you concatenate every row into a long vector. Then this is the input for your autoencoder. And at the beginning, what will you do at the beginning? Well, you have now your images. You have asked ChatGPT to convert your images into long vectors, such that you can train your network. So actually, ChatGPT would create matrices out of it for you to use some PyTorch library or scikit-learn to train your neural network. What would be your next step? Yeah, let's say the architecture, you also define it. Yeah, also good point. There are many, many parameters of this architecture. Let me go back. Here you see it. For instance, it's indicated by this symbol here. This symbol is a sigma. It means the sigmoidal activation function. It's a very nice, well-defined, mathematical, well-defined differentiable equation. So we love it a lot in machine learning. And that's what you also decide. So these are design choices. But the first step is normally you need to initialize your model. So your model will convert any input into some output. And it does that by passing the information through some neurons and through forward propagation of the information. We will come to that. I have some detailed slides on that, but you need to initialize your model weights, your model parameters. That's the first step. Okay. Now, in the beginning, your reconstruction will be really poor, but throughout the training process, your model will become better and better. And in the end, your autoencoder reconstruction will look like that. It will remove all unnecessary details like the logo here or the text, because it does not have the power to represent that. What do I mean by that? No, it's the representative power of the model. This is the key concept in machine learning. How complex does a machine learning model need to be to explain your data? In autoencoders, you make use of that. You decide that your narrow passage compresses the data. If you only have 3 neurons here, you won't be able to reconstruct all details because your model is not complex enough. It does not have the computational power or the power to represent the data sufficiently well. And that's the reason why here these details are gone. And in the last row because it was 91. Back then, PCA was state of the art, the state of the art dimensionality reduction technique. What does PCA stand for? What do you think? Any idea? Yeah, exactly. But PCA is an acronym. These three letters stand for some terms. Yeah, but who knows what's the name of this algorithm? PCA is only the shortcut. It's called principal component analysis. It's a matrix calculus-based reconstruction or dimensionality reduction technique. We will do some matrix calculus throughout the course, but we won't cover PCA. Okay. Yet, let's talk about a different application. This is a classical facial detection problem. And let's look at this algorithm. This algorithm was developed by Viola and Jones in 2001. It's a very popular computer vision algorithm. It was a popular one back then. We call it nowadays the classical computer vision algorithms. And the key idea is to use some patches. These are masks that we use. We predefine them. We as experts, we say we would like to have these masks because they are best. Then you use them and you move them around along your image and you compute values, scores. And these values that you compute are called features. So in the end, what you do is you convert a face or an image into a long list of numbers, which we call feature vector. This feature vector is now the representation or the substitute of the image. And now this particular algorithm uses a cascade of deciders, of decision steps, to in the end say this is the face of subject A or B. Now in 2001, actually, this Viola-Jones face detection algorithm really achieved remarkable success rates. Back then, above 90%. Nowadays, don't nail me down, these numbers are outperformed by deep neural networks. So there's a different thing that is called face recognition. You should at least know what's the difference. This is also some minor detail. Face detection means that you identify individuals. Recognition, no, sorry, wrong, opposite way around. Face detection means you detect faces. This is a face, or this is a car, this is a bike. Facial recognition means that you identify the person X. Good. This is forgive me for the mistake. This is an example that we developed ourselves in our research group in 2016. Here we develop probabilistic time series models, so machine learning approaches, and we were always looking for interesting applications where we could use our machine learning methods actually to answer some research questions. And that was a particular interesting research question. The key question was, if human subjects interact with the environment, well, we make contacts with the environment. And some of these contacts help us to maintain our stability. We don't fall down because we lean next to the wall if it's dark, or if we reach out for something, it's really far, we make this additional contact. Now, the research question was, do we really think about where do we touch something before we do it on a millisecond time scale? Or is it just some random behavior? We simply do something, we need to lean on some table and it works out like that. That was the question. Now, this question sounds simple, but answering it is not simple. It means that we need to record data, and model the data. And that's what you see here. You see here that we try to understand if the individual motions of parts of our body, like the trunk, the wrist, of the left hand and the right hand, if these things are somehow coordinated together. And if these supportive contacts would be planned or pre-processed process, then I can precisely predict from the supportive contact what you would do. And that's illustrated here by the lines of the left wrist and the right wrist, because the subject were standing in front of a large screen, you see it on the left, and they had to touch one of these dots with the right hand. With the left hand, they had to make a supportive contact. Well, actually, they would fall over without that because the screen was very far away. And actually, we really adjusted everything to the subject height. And what you see here is a simple illustration where we said, okay, let's assume that we only observe the trunk motion and we try to predict everything else. We predict what the right hand will do, what the left hand will do. And you see here in dashed lines, the true data, that was the training data. And in blue lines, you see the model prediction. And the closer the match is, the better is our model. That's what you see here. What you also see is that, well, a single experiment would not be very strong, or the results of a single experiment. You need statistics. And in machine learning, we compute these statistics and we visualize them for trajectories using these confidence intervals. You see these shaded regions. And in this case, this is the statistic is shown over, I think, 20 different runs. And I'm not sure if I have it here. Well, short answer is yes, it's really some pre-processing process that is involved because it's not random. It really correlates. If you touch something on the right side of the screen, your position on the table is also reflected. It does reflect that. So it's more to the right. And we also found out that actually, even after 100 milliseconds, so prior, before any visual feedback could be processed by the human brain, because that takes about 300 milliseconds until your eyes turn our lights into some electrical signals that can be processed by our brain. That takes 300 milliseconds. So even prior to that, this correlation holds. Otherwise, one could assume, well, yes, supportive contact and the point on the screen, they are of course correlated because you see it with your eyes. Well, you do see it, but it takes 300 millis until you know it. Okay. Here I show you a model, the model that was used in this research. So in machine learning, we talk about models, always. Every week we talk about models. Now I show you some model. You see here, the first plot here shows some Gaussian functions. We call these functions basis functions because they are also something that we decide early on. We say, let's use these kind of functions because they work best for us. So it's also an expert decision. Then there are some features that can be learned. And if you multiply these two things, you can reconstruct any nonlinear function that you want. You again see here that the reconstruction error depends, of course, on the number of basis functions. So a very expressive, complex model would have more basis functions. A very simplified model might work with 3 to 6 basis functions. In our case, we worked, I think, with 6 or 10. I don't remember it exactly. Now, the trick in our approach was to simply concatenate the individual dimensions of the right hand, the left hand, the trunk, of all dimensions X, Y, Z, into one long vector. So everything is a long vector now. And if we do that, we can compute statistics of such vectors because we have for every trajectory, we get one vector. Now we can compute the mean and we can compute the covariance. And if we do that, we can model the correlation between individual body parts and the time. So actually we model the correlation in time and in space with this model. And the result is an infinite number of trajectories. You can create with the model now infinitely many trajectories. That's the model. It's a generative probabilistic model. That's a bit easier to digest. Here you see the ICAP system. The ICAP system has 53 motors. You see it here, it's a bit shaky because when I did the experiment, we already worked for the whole day together and everything heats up. And at some point, the system becomes really shaky. In this research, I used the same model on data that was recorded through teleoperation. So I teleoperate the system, but I record the data in the robot coordinate system. So I got data from the joints of the robotic system, from the fingertips of the robotic systems, from tactile sensors. That were my model data. Afterwards, I trained this probabilistic model, and then I could use this model to reproduce the behavior. And what you see here is now the mean of my trajectory model. It's just the mean. And I could, in principle, execute this behavior now infinitely many times. So these models are really powerful. If there are no questions, I will simply continue. Let's talk about autonomous decision making. So at DeepMind, you might have seen these stellar results that DeepMind proposed in 2015 in a Nature article, that their models outperformed humans in playing Atari games. Maybe you have seen it. Now, the key idea of this approach was to map pixel images from the computer game into a state of the agent and into motor commands. And the motor commands were actually the joystick commands. These commands were also binary, move to the left, to the right, A, B, C, these buttons. So everything was discrete. And it looked like that they had a very large neural network, and they converted the pixel image into a long vector. This long vector was used as input. Then they had different activation functions indicated by this circle here. And in the end, they had some readout layers, fully connected layers, where the networks were trained, the network weights. And the output of the model were the actions. So inputs were the images, outputs were the actions of the joysticks. And they could immediately connect the outputs of the model to the joystick, or replace the joystick, actually. I think I have a video. I have two. Here you see how the model learns to play Space Invaders at different time steps. You see at the beginning, tries to avoid being shot, but it's not so performant, I would say. But during the training, so with the progress of the training, it becomes better and better. What is the signal that is used to guide this learning process? How is the model improving itself? What do you think? And where is it, the reward? The points, exactly. So this is one benefit of these Atari games. You have a score that reflects your performance, you can immediately use it to improve your model. We call this a reward signal. And it's a very interesting result. This is another game. I like it a lot because it learned a very clever strategy at the end. Take some time. Yeah, here you see it. This is now the final strategy that works best. It's pretty clever. Any idea what could be a proper state of a neural network in such a game? What do you think? We said this model converts pixel images into actions. And it needs some kind of state representation, yeah? Yeah. So this is pretty interesting. Classical reinforcement learning would model an action space. This is easier because you can only move to the left or to the right in this game. But you would also need to decide what is a proper state definition. Also, this space needs to be defined. And here we had this small ship or whatever it is, small element that was moving around and had different space locations in the space. This is the state. And there's another thing that is defined by the state that's actually where the blocks are in the space, how many of them are left. All these things would need to be somehow encoded into some long feature vector. This deep neural network actually did something very smart. It said, oh, let's try to avoid defining this state explicitly. We just define the action space. We just use the input, the pixel images, and that's it. And the network itself will discover which state representation is necessary to improve the score. Today I'm a bit slower than last year, but it doesn't matter. Some of these details are really interesting and exciting to share. Here you see the summary result of this paper from 2015. That was really a game-changing paper back then. And you see that they really did a very good job in advertising their achievements by saying, look, we as humans, we believe that we are the smartest subjects, brains on this planet. But look, this is human level. And here, some of the games we are above human level with our deep neural networks. What is not discussed here? What is the major difference between here, these deep neural networks, and human beings? For each of these computer games, a single neural network was trained. And it only works on a single game. A human player would learn every game. And regardless which game you play, immediately after a few milliseconds, you would be the expert. You switch. So here, expert systems have been trained for particular games, computer games. This is also very interesting. This figure, I like it a lot. This illustrates or tries to illustrate the state representation. And if you look at the paper, they will also discuss what you could observe. Well, there are some clusters where you see a particular state for Space Invaders, which describes some particular scenario or situation. And then there are some other clusters that are different. Well, I don't play Space Invaders. I don't know the states and all these details, but I understand what they want to tell us here. This is a two-dimensional representation of, I don't know how many parameters they had, probably 10,000, 100,000 different parameters were reduced in dimensionality into a two-dimensional space. And the color, so maybe it's three-dimensional. So, what I can tell you now, keep on reading. If you're interested, there is a lot of exciting literature out there. Have a look. There are some links that are really interesting to look at. Keep on practicing. Create accounts on our Jupyter Hub notebook. Work with it. Free to use. Now, I have prepared a quiz without bonus points. Sorry. Now we will look at the examples again, and you will tell me what type of machine learning algorithms it is. I promise you there are three types. One of them is called supervised learning. In supervised, let me switch to this slide. In supervised learning, we have inputs, we have outputs, and we compute always some error signal. So for instance, we know that this is a cat, this is a dog. I can compute an error signal. It might be a 0 or 1. And with the error signal, you can improve your model. That's supervised learning. In unsupervised learning, we just have data. There are no targets. There is no error signal. We only have data. We can use data to compress it or to visualize it. But that's it. And the last category is called reinforcement learning. Here, we might get from time to time some reward signal. In the Atari games, we had the score. Yes. But in principle, it could be way more challenging. You could play a game like tennis for 2 hours, and at the end, you win or you lose. You won or you lost. So after these 2 hours, you can try to improve your model with thousands of actions. That's typically reinforcement learning. Here are some examples. I skipped that now. Now, question to you. This example, to which category does it belong? Unsupervised. Correct. Next, facial detection. It's a bit harder. Supervised, yes. This one, time series prediction. I also did not explicitly mention it, so it's a bit harder. You can also guess. Here it's okay to guess. Not for the final exam. Well, you can, but it's difficult to pass. Supervised? Yes. It's supervised because we are using training data, these trajectories. We are training these models using basis functions where we reproduce the original data. Remember, I told you, if I increase the number of basis functions, I can reconstruct this nonlinear function precisely. So I computed the error signal between these two things. Yes? Excellent, excellent. I like it. It's part of the interactive learning component, which is also part of reinforcement learning. What you describe, we at our chair, we're actually investigating such learning algorithms. So one of my PhD students, he tries to come up with novel learning methods that would identify or decide when to ask a human being. So the AI system tries to solve a task, a game, like reinforcement learning with some reward. But there is a human expert. And whenever the AI system recognizes, well, I don't make any improvement anymore, or actually it's so uncertain, my current state, I have to ask the human. And phrasing that in mathematical equations is really interesting. That's what we are doing. So this is called interactive learning, this topic. There's a subfield called preference learning that also goes in that direction. I show you two solutions and you decide as a human expert which one is better. So I'm the AI system. The AI system says, well, I have now three solutions. Please, human, tell me which is the best. Based on this feedback, the model is improved. And there are all sorts of combinations. That's true. There's this motor skill learning example, which is also trajectory based. So this is also supervised learning. Then we have decision learning. Exactly. We mentioned it several times already. That was a bit easy, yeah? Okay. Then I don't know why this is bold now. If we have time, yes, I talk a little bit about the human brain. I did my PhD in 2010. I started, and I did my PhD in a computer science lab where our main ambition was to understand how the human brain implements functions. And we know a lot about the organ, the human brain, the weight, the size, the chemical processes, the neurotransmitter. We know a lot about it. But if I ask you, well, how did you actually solve this differential equation in your human brain? How many neurons did you use? How were these neurons connected? This is a challenging question. We don't know it. Actually, we can't even measure it because whatever we measure using different measurement devices, regardless if it's an electrode array or some surface fMRI study, it averages over 10,000 of activity signals from neurons. What you get is an activity pattern that says, well, okay, this brain region is active. With arrays, you put needles into the brain and you actually destroy many neurons. Some of them you might detect then the activity of some neurons. So there you get better high quality signals, but this is also difficult to do with humans. I'm not sure if it's allowed at all. I don't think so. But this kind of research is really interesting. The human brain is the most powerful computing system on this planet. And we know so little about it, despite these facts that are listed here. So what I did then was, well, I can't test if my model would work in human brains. I can't test my model. Doesn't work. What I can do is I can train a model. I can test it on some artificial systems like some humanoids. And that would help. And that would work. So the human brain is an inspiring organ for millions of researchers. And one of the most well-known, most popular systems, models nowadays are neural networks. And I promised you that I will give you some details about these neural networks and about how information is processed in these neural networks. We use throughout this course typically some notation where we say inputs are denoted by this X label. weights are our free parameters, denoted by W. And there are some activation or transformation function. Here it's called sigma. And we have some outputs of this model. Now, in mathematical terms, I can say the output is given by a function called sigma that takes as input the product of x times w. That's the mathematical function that is implemented by this neuron. It's a single neuron that multiplies these two elements, passes it through this transformation function, and produces the output. Now, what I can do is I can compute the derivative of this transformation function, which is very nice if it's a sigmoid function. So you see it here for this sigmoid function, you see that the derivative is simply the function itself times 1 minus the activation function. Now, to make this thing a bit more powerful, we add another free parameter. Free parameter means I can train this parameter. I can train it from data. This free parameter term is called bias or offset term, and it's simply added here to this product. Now, defining large networks using this equation is really tricky. So we needed something more convenient to describe complex models with mathematical equations. And the answer was matrix and vector calculus. And that's the reason why in the whole course we will use a lot of matrix and vector products. And you see it here. I see that we have now 3 inputs, 3 W parameters that we can learn, and a single bias term. I can say now, okay, the output is given by the transformation function of x times w transpose. This is the transpose operator plus our bias term. Question to you, what is the dimension of the output? Who says it's a vector? Raise your hand. Dimension 3. Who believes it's something else? It's a single scalar. It's a number. Exactly. Because in the end, what you do is, so this is not the nice way of using blackboards, but I think it's okay for today. The output is given by x1 times w1 plus x2 times w2 plus x3 times w3 plus b if the activation function is the identity function. My model is now even simpler. Sigma is 1. Sigma of x is the identity function is equal to x. Or 1 times x, whatever you want. So it's a scalar. Now, even this notation is not so nice to create complex models, so we can even simplify it further. And this is a very popular exam question where I ask you, well, how can you combine this bias term into the vector notation? And then the answer is simple. You say, we can use an additional input. We can use 1 as input, and it's always 1. So the first input is always fixed and set. It's clamped, we call it clamped, to 1. And in this case, the first parameter, W1, is now our bias term, B. So what is the key idea? The key idea is to minimize some error, some objective function. Also, this term objective function in machine learning is used to say, okay, this is something we want to maximize or minimize. Sometimes it's called loss function. So these are the objectives that really are used to improve the model. In this case, I have here the Euclidean function, Euclidean distance, over some signals O with some targets T. And I have K elements, K target values. So now in the vector notation, I can say I have this transformation function of our input times the parameters, and I compute here the difference to our target for a single value. For a single value K, that is nice. And for a single value K, I can now compute the gradient. I can say, okay, for example number 304, the error is 10, which is very large, but how can I improve now my model? You can say, okay, how would the model perform if I would increase or decrease my weight W a little bit? And this question is called computing the derivative. If you would increase the weight, is the error higher or is it lower compared to this previous number? With this information, you can actually say, okay, now I know that I have to increase my weight number 3. Then the error will be lower. So you have a gradient. And what you do in machine learning, I say, okay, let's do that, but only with a small step size, a small increment. Be careful. And this small step size or small increment is called learning rate. And this is sketched here. You see that we compute for a single sample the error. It's this dot here. E of W is the error. And we compute the gradient such that we know in which direction we have to improve our model. And then we do that for every subsequent example. And these are the errors. And we do that as long as we still can improve our model. This algorithm is called gradient descent algorithm. And it converges to a minimum. In this case, it's called the global cost minimum. Can somebody explain why in this case it's really the global minimum in this sketch? And what is the difference to a local minimum? Exactly. Do you know what is the mathematical property that is necessary to say that it will converge to the global minimum? Nope. That's the reason. For a convex function, there is only a single minimum. You see it here. And therefore, this gradient descent algorithm will converge to the global minimum. But in practice, in general, this is never the case. Your error function will be super complex and your algorithm will converge to some local minimum. And that is the reason why most machine learning algorithms got stuck in the past, because we had little training data and we started with some models that were not stellarly pre-trained like nowadays. And then training converged to some local minimum. The performance was okay, but facial recognition, for instance, it was still far behind all of these mask-based approaches. That was the time where we had the cold winter, neural network cold winter in the 80s, 90s. So here you see the update equation. I skip it. In the end, if you compute this derivative, you can do that in closed form. And you can apply these iterative updates. You see that here. So these weights are updated after every single sample. And here the learning rate is denoted by this Greek letter eta. So nowadays, these updates are not performed after in a single sample. Say you have 10,000 images, you use batch sizes of, let's say, 200 images. You compute for each of these 200 images your error, your gradient, and then you compute the average of the error and the gradient, and then you perform the update. And the reason is that simply stabilizes your training process. It's less likely that your updates will converge to a local minima because you consider not only a single sample, consider 20 or 200 samples. The larger the batch size, the faster is the training speed. But what is the drawback? Why don't we use large, super large batch sizes? Nope. At our chair, we also have this restriction, and my employees constantly argue that they need more of something because they can't increase their batch size. They need the memory, the GPU memory for the batches. You need to load the whole batch into the GPU memory. And that's the reason why sometimes we can't compete with Google, OpenAI, DeepMind, or can't even compare to their results because we can't implement their models and their batch sizes. Good. I think I skipped that. We are at close to the end. I'll show you something here. Well, if you don't implement batch updates, there's another big risk, and you see it here. This is a very smart, nice behaving example, but you already observe in this simpler example, if you try to differentiate between the blue and the green dots by defining a single separating plane with this line, and you compute the error, how many of these dots are correctly assigned to the left or right side, or to the green group of green and blue dots, then you will see that if I update my model after every single new dot that I look at, it will move around. It becomes unstable. So the model updates are unstable if you apply updates after single samples, because the samples are also prone to noise. With the batches, you average over the samples, you average over the noise. Updates become more stable. And there are many, many more techniques nowadays. So one of the reasons why AI breakthrough was so strong in the last 20 years was because we have more computational power, yes, plus we have many more tricks now. We have pre-trained models, and that really helps improving it. There's another interesting example that I want to show here. This is an unsupervised learning algorithm, one of the most popular ones. You don't see it, sorry. This type of algorithm is called clustering algorithm. So you have given endpoints, and you know that, well, these points belong to 5 clusters, like the grades that you can get in this course, 1 to 5. Now you would like to cluster them. What you will do in this example is that you place 5 initial random seeds in the space. These are the black crosses. And then you look at the distances to all dots nearby. And you assign each dot to the cluster that is closest. Then you update the cluster mean, the XY coordinate of these black crosses. And because you updated, you moved around the black cross, now you have to reassign all the dots. And this process continues until it converges. And the result looks like that. Here you see the individual iterations. And quickly these these black crosses converges to the cluster centers. In machine learning, one of the most important things are assumptions. There's one big assumption in this example. Who can tell me which it is? We spot it. Yeah, more in detail. Yes, this is the biggest assumption here. You need to know how many clusters you have. For some examples, you know it. For others, you don't know it. So you have to play around with different numbers of clusters. And the second thing is you need to create these initial seeds. And if you have a very large space, maybe it's not just two-dimensional, maybe it's higher dimensional, then this algorithm does not work anymore very well. Okay, I want to come to an end. There are so many more results to show, but let me summarize what we did today. So this is my last slide. We talked about 3 categories of algorithms. Let me unfold everything first. We have seen that supervised learning algorithms require a target or training signal. You compute some objective functions, some Euclidean distance. Based on that, you can compute an update signal. And the key idea is to minimize this objective. We have seen unsupervised learning examples where we simply use the data as it is, like here. We pass the data through some autoencoder narrow passage to compress it, to remove the noise. Or in clustering algorithms, where we just want to find similarities in the data points. Do they belong to the same category, same cluster? This is unsupervised learning. And the last category is reinforcement learning, which is among the most challenging types of learning algorithms, because here we get a reward signal, a sparse reward signal from time to time. So maybe after one action, maybe after 1,000 actions, and then you have to decide what to do. The truth is actually designing these reward functions can be as complex or even more complex than training the reinforcement learning algorithm itself. With that, I would like to thank you for your attendance. Next week, I will complete this fundamental section by talking about very important machine learning concepts, problems, topics. After that, you will be able to discuss that with research colleagues, with machine learning experts, and you will know what's a long tail and a big tail and what is overfitting and all these things. Thank you for being here. If you have questions, I'm still here. I'm looking forward to see you tomorrow on Friday. If you're a programming expert, feel free to skip this event.